We already talked about rotation matrices and homogeneous transformations. Now let's see how to use them. And let's go back to a familiar example, our 2R manipulator or planar elbow manipulator, and see how we will use the ideas we have just discussed. Okay, so to reiterate, two links, link length L1, link length L2, two angles Q1, Q2, and we are still sticking with our absolute angle Q2 here, even though that is not natural when you go to a more general situation. But that's fine, since we are familiar with this setup, let's stick to this. And the question is, you want to calculate X and Y in terms of Q1 and Q2. We already know the answer, we have worked that out, but let's see if we can do the same thing using rotation matrices and homogeneous transformations. Now the big difficulty in applying these transformations is that you have to first figure out how to define the various coordinate frames, and that is something that the user has to do. There is at the moment no standard recipe to do that, but once you do that, the theory we just discussed gives you the advantage of just setting up a bunch of matrices and multiplying them together to get your answer, right? So let's go through that. So let's start with our base frame, and this you typically would want it having the origin at the base. So let's define this frame x0, y0, z0. So this is the 0 frame, inertially fixed at the base, nothing is rotating. The x axis of this frame is pointing out of the plane of the board, and y and z are in the plane of the board. Now we need to calculate P. So obviously we need to figure out, what transformations need to happen to this frame to go to the next joint and eventually to P, right? So another natural choice of second frame would be, let me take the black color to do that, is if I simply take the same frame but rotate about x axis so that the new y axis is aligned with the link direction. So let's call this y1, and then this would be z1, and since we rotated about the x-axis to get this new frame, the new x will still be collinear with the old x. So x1 will be the same as x0. So what did we do? So we had a frame here. So imagine this is x, y, and z. We rotated about x-axis until we got a new frame that is aligned with the link direction, or rather y of the new frame is aligned along the link direction. So this is our one frame. So this was our 0 frame, this is now our 1 frame. Okay. We'll come back to this, but let's set up one more frame. Likewise, if we had to have another frame aligned with the second link, then we would have yet another frame, but this time the origin will be at O2, and this would be y2, z2, x2. Now just to repeat, y and z are still in the plane of the board, x is still pointing out of the plane of the board. So really x0, x1, x2 are all pointing in the same direction, right? So in terms of transformation, what needed to happen to take the one frame and transform it to the two frame? We needed to first, now this is where homogeneous transformations kicks in, we needed to first translate it to a new origin and then rotate it further by an additional angle to align it with the link direction. Okay, now let's go through and think about a bit more specific of how the math would look like. So the first part R0 to 1 must be obvious, because what did we do? We simply took the 0 frame, rotated by x about the x axis to get the new frame, and what angle did we rotate it by? Angle q1. So what is this? This is simply the standard or basic rotation about x by angle q1. Right? We have already seen what that matrix looks like, so we simply plug in q1 over there, and that we get the rotation matrix. Here there is no translation, right? So if we were to think in terms of the more general homogeneous transformation, then d0 to 1 is simply 0. Now what's happening between one frame and two frame? I have the one frame, then I'm translating along the y of the one frame by a distance L1, and then rotating by a further angle, and rotation is about x-axis, right? So if I think about R1 to 2, the rotation part of it is simply a rotation about x-axis again, but by what angle? Not by q2. Did you guys think for a second that the rotation is about q2? No, because the axis was already at an angle q1 and you are reaching q2. So really, this is still again a standard or basic rotation about x, but by angle q2 minus q1. Right? So we again can take the basic rotation matrix equation, plug in q2 minus q1 for the angle, and we would get this rotation matrix. And d1 to 2 over here would be the translation that we did here. But remember, d1 to 2, the assumption is it is still expressed in the first frame before the rotation. Right? So in this case, that would be the one frame. So in the one frame, the translation is L1 along Y1. So if I were to write this, let me give myself a little bit of room. If I were to write this in terms of the vector coordinates, this would be 0, L1, 0. Why is that? Because L1 is along the Y direction. That's it. And there's no translation along the X and Z direction. And all of this is resolved in terms of the one frame. So that's why I'm just looking at the one frame and the coordinate of the translation vector in that one frame. Okay. So we have the 0 frame, 1 frame and 2 frame, but we have still not figured out how to solve for x and y. For that, we need one more step, which is, since the end effector is fixed relative to the 2 frame, because 2 frame is now fixed rigidly with the link 2, then I can go ahead and actually write P, but in terms of the 2 frame. Now what would be the coordinates of P in terms of the 2 frame? Again, a similar idea. Since y is always along the link length, P would always be L2 away from the origin of the 2 frame and in the y direction only. Right? So P2 is just L2. And that's it. Once we do this, then what do we need? We need to be able to calculate the coordinates xy of P in terms of an inertially fixed frame that has origin at the base. We need to be able to calculate P0, and in terms of the homogeneous transformations, we will add an artificial 1 here, and we would get h0 to 1 multiplied by h1 to 2 multiplied by P2 1. H0 to 1 we have figured out already. We can use both of these to write the homogeneous transformation matrix, and then H1 to 2 we have figured out. We can use both of these to write that matrix. That's it. So this gives me complete forward kinematics for this. So the math is fairly straightforward, but as you could see, the difficulty is, first you have to think through what are the coordinate frames going to be, and you have to figure out how to define them, where the origin will be, how much will the translation be, and so on and so forth. Now let's look at just one or two more things here. This is simply how we chose to do it. Another user could have decided that, you know, 0 frame is okay, 1 frame is okay, but in 2 frame I would, instead of, for whatever reason, they thought maybe it's not a good idea to align the link with the y direction. So from the 1 frame they said, okay, what if I do a translation along y, then rotation about that y, and then another rotation to align the y with the link length, right? Did you catch that? So I'm going slow here. So let's take a second again to do this. So 1 frame is here with x pointing out of the board. You translate along the y, and then you rotate about the y, so that now the z axis is pointing out of the plane of the board, right? And then you rotate about z so that the y axis is aligned along the link. So that, if I could use a different color, let's use blue, then that would mean that I still have my y pointing along the link, but now my z is pointing out of the plane of the board, and my x is perpendicular to y and in the plane of the board, x2. So what I'm trying to show here is somebody else could have defined this coordinate frame differently, right? Without thinking about it, they may have thought, okay, it would be good to have x, y in the plane and z pointing out of the plane, right? So my coordinate frame looks like this, or rather, sorry, like this. So z is pointing out, y is along the link, and x is in the plane. There's nothing wrong with that, except that you can see that the transformation to from 1 to 2 is now a little bit more complex. You have to do, rather you had to translate, rotate, and then rotate again to align. So you had to do 3 operations, and this is where you would use, we talked about, you can think of a more complex rotation as a sequence of simpler rotations, and the technically correct word there is really composition. You can think of a more complex transformation as a composition of simpler transformations. And what is the difference between sequence and composition? Sequence has this implication that it happened in a certain sequence, right? Composition means it may not have happened in that certain sequence. You may have had some kind of, no, not in this situation, but in some other situation, you may have had multiple motion together, but then you compose that, or you think of that as first one and then the second motion happening later. Okay, so in any case, we could still do this, but in this new choice of frames, H1 to 2 will again have a composition of 2 rotations. So this helps highlight the fact that if you are not careful with your choice of axis, then your problem and how you set up your frames, how you set up your transformations can become challenging. How do we deal with this? And this is still just planar. If we go to three-dimensional robots, believe me, this can be super confusing. Okay, so how do we deal with this? It turns out that's where DH will help us. DH is Denavit-Hartenberg, and this is a standard way to set up coordinate frames for any robot, and that also gives you a standard recipe for, first of all, how to define the frames, and once you define the frames, then how to work out all the transformations. And that's brilliant. Once you do that, then you can simply put it in a piece of code, and then any new robot you have, all you need is the DH parameters, and you can reuse the same code for any new robot. That's what we'll talk about next.